This is operating systems discussion on deadlocks, right? As you can see from the picture below shows a deadlock, usually a gridlock, but deadlock is worse because nobody can do anything. So looking at the picture here, you can see the cars can't go forward, and they really can't go back. And what they are sharing is the road. It seems to be a roundabout of sorts. But nobody can go anywhere because everybody else has blocked someone else. And you can see this in a lot of traffic situations. So a deadlock just means there's no progress because everybody is waiting for something else. Right. So for deadlocks to occur, there are at least 4 things that we talk about. First is mutual exclusion. Means something is restricted to a limited number of users. Mutual exclusion. Another thing is hold and wait. Hold and wait means someone has a resource and is waiting for another resource to proceed. Right. Another thing is no preemption. No preemption means nobody is allowed to tell the other person to let go or restart. And the last thing is cyclic waiting. That means one person is waiting for something that in some cyclic way everybody else is waiting for. Right. So let's look at the first one, mutual exclusion. If you look at this road we have here, everybody has a spot and his spot cannot be shared by someone else. So if you pick this car, the car behind him can't share that spot. If you pick the black car, that black car can't share the same spot with someone else. You know, if we wanted to prevent mutual exclusion, maybe we could have flying cars so that the space could be shared vertically. So one car can fly over the other car. Then that would solve the problem. So looking at this, these are the conditions for deadlocks. If we can break any of these, we can solve the deadlock situation. Mutual exclusion, that's the first one. If we have a space, so if we have a square on the street, is it just that one car can go through? If only one car can go through, we have a deadlock problem as we have now. But if maybe some cars could fly, remember the Jetsons? I don't know if you've seen the Jetsons. So in the Jetsons, cars were able to fly, meaning they were not stuck to one spot on the ground. So that would solve mutual exclusion. What about hold and wait? One person is having one part of the street and is waiting for the other person to let go. So you can pick maybe this car here. It has this car, but it's waiting for this part of the street before it moves. This car is waiting for this part of the street before it moves. So that is hold and wait. That means you have a resource and you're waiting for the other one. No preemption, right? So what if we could tell a car to get off the street, right? Or maybe we could pick a car and maybe use a crane to move a car from one spot to the other. The way this thing looks right now, that seems to be the situation. Alright, so hold and wait. Or no preemption. No preemption means if we are not allowed to take a car off the street by ourselves, maybe take this and move it somewhere else. Maybe with a helicopter, pick one car and drop it somewhere else. Then we can make spaces so that there can be progress. So no preemption means processes that are running cannot be stopped and their resources cannot be taken away from them. Usually by killing a process, you take the resource. But it would be interesting if you can take a resource from something, then you could have progress. Cyclic waiting, you can see this is a cyclic waiting. One person is waiting for this, he's waiting for that one, waiting for that, and it forms a cycle. Right? And cyclic waiting can be much simpler. Maybe Kofi is waiting for a bowl from Amma, and Amma is waiting for a spoon from Kofi. Now at this point, I believe Kofi and Amma are going to starve because someone is going to get any food. But what if we could tell Amma, let go of the bowl? Oh, well, Amma has a spoon. So Amma, let go of the spoon. That will solve the issue. So that means 4 conditions. Mutual exclusion. So for any deadlock situation, you can ask yourself, mutual exclusion. What if we told them Kofi and Amma can eat from the same bowl? right? Right, that's one. Hold and wait. That means Kofi is holding on to something and asking something from Ama. Ama is holding on to something and asking for something from Kofi. So if you allow someone to hold something and ask for something else, then you have mutual exclusion. So one of the solutions to this is in some computer systems, what they'll try and do is a process can try and grab all the resources it needs. So if Kofi needs to eat, he has to get the bowl and the spoon before he tries to do anything else. Else he should sleep and let go of everything so someone else has to go. So there are ways to solve this hold and wait scenario. You can also have cyclic waiting. Cyclic waiting means people should not, if you want to solve this problem, it means solve means prevent a cycle, right? And that means, for example, if you look at this street, maybe this car, that's the white car, should not have gone knowing that if he goes, nobody else can go around the roundabout. So sometimes you can just, the computer can predict and say, well, Amma wants to take the ball, but I know if I give the ball to Amma, then Kofi is going to be waiting for the ball from her, and that will create a cycle. So it's possible for a computer system to, in terms of detecting cyclic waiting, can make a dependency graph showing who is waiting for what. And if you can make such a graph, then you can predict, even before the person starts to ask for the resource or acquires a resource, that is going to create a problem, right? And there is no preemption. So to solve no preemption just means we have to be allowed to take something from someone. So in the case of Kofi and Amma, we should be able to take maybe the bowl from Amma or take the spoon from Kofi and give to Amma, right? So these are the conditions for deadlock. Right? If all four of them hold, then there's really nothing you can do. A deadlock will occur. But if you can at least solve one of them, then you could have solved the deadlock problem. Now, one of the algorithms discussed is the banker's algorithm. Now, with the banker's algorithm, every process has a representation. Maybe needs two cars, three drivers, needs four accountants. Right, so I have here listed, trying to illustrate the banker's algorithm, four processes, each one listing the maximum number of things it needs. So if we have three cars and three drivers and four accountants, we should be able to satisfy this problem. So for example, we could say, let process C go first. So process C will pick three drivers. That means that, so three cars. If process C goes first, there will be no cars remaining. There will be one driver left over and one accountant left over, right? And then process C can finish. If process C finishes and then releases the drivers, then we can tell process B to go ahead, right? And process B can then pick one car and leave two cars over, can pick two drivers and then leave one driver over, and pick two accountants and just leave two accountants over, right? So anytime you look at the current distribution of things and you know that you can make progress, then you are in a safe state, right? Now let's discuss a case where there's a deadlock. Suppose process A currently has two, let's say one car, it's holding on to one car. Process B also has one car, and process C also has one car. Nobody wants to let go of their car, right? That means there's going to be immediately a deadlock, right? So this is unsafe, right? Meaning that as things stand, if you only have 3 cars, process A would like to have 2 cars to finish their project, wants 3 drivers to finish their project, and 4 accountants to finish their project. Similarly, process B wants 1 car, 2 drivers, and 2 accountants. Then if everyone picks 1 car each, they are now in deadlock, right? So in the banker's algorithm, the idea here is you should be able to, before you give someone resources, look at the maximum number of things they would ever need and try to determine if given those resources, the person can proceed to completion. Of course, the simplest solution is let only one person have access to all the resources and finishes, and the next person and the next. Right? But usually, depending on how the things are distributed, you might be able to find a way to allow one person after the other to go through and finish so that you wouldn't have a deadlock, right? So in most operating systems, this can happen because maybe there's memory, there's a sound card, there's a video card, there are many resources, and you have to decide who can go first, right? So with this, we've just briefly discussed just main ideas in deadlocks: mutual exclusion, hold and wait, no preemption, cyclic waiting, and if you can prevent one of these, we can solve the deadlock problem. But of course, we have to have some way to keep statistics on what people need, and we call this the banker's algorithm. I don't really think it has to do with bankers, but it's called banker's algorithm. It just means keep statistics of what people need and check to make sure that before people ask for things, you can satisfy their requirements so that they don't end up in a deadlock. And the example here is if process A needs 2 cars to finish a project, process B needs 1 car, and process C needs 3 cars, but you only have 3 cars. If you give each person a car, each process a car, you end up in a deadlock. But you can let process 2 go first. Maybe give them the 2 cars, let it finish. After I finish, you go to process B, you have 1 car, and process C, you have the 3 cars. So that is just a brief overview of deadlocks.